Okay, so we want to finish up the log normal size distribution in our unit on sizes. So I want to start for that with this size spectrum that we looked at in one of the early sessions. So now we've defined the log normal distribution and its parameters, but when we started talking about aerosol sizes, we said aerosol are multimodal. And so they span this very large range of sizes, and they have peaks at what we call the nucleation, Aitken, accumulation, and coarse modes. And then we also have a variety of different aerosol sizes that kind of locate in different parts of this size spectrum. And so if we want to describe the full range of aerosol that we have in the atmosphere, then we will need multiple log normal distributions, a different log normal distribution for each of these modes, or alternatively for each of the different aerosol types. And so what that looks like in practice is like this table, which is not great resolution, but you can see along the top that there are 3 different modes, 1, 2, and 3, which might correspond to the Aitken accumulation and coarse modes of aerosol. And then in the table, for each one of these modes, you have your normalization factor, the total number, and the 2 parameters of the log normal size distribution. So the geometric mean diameter and the geometric standard deviation. And then you have that normalization factor, center of the distribution, and spread for all the different types of aerosol that you see kind of down here. And so this is what an aerosol module or an aerosol scheme might look like within an atmospheric model. You have this kind of table of different parameters for different modes and different aerosol types. So with that, then I want to talk a little bit in a very zoomed out way about chemical composition of aerosol. We're going to come back to aerosol chemistry in the second part of the class more rigorously. But you saw on that table then that there are these different classifications of aerosol, and I want to talk about those in a little bit more detail. When we started the unit on size, we talked about the relative contributions of natural versus anthropogenic sources. We used this table 14.1 from Hines and said there are very large kind of uncertainties associated with the total mass of aerosol in the atmosphere per year, but in general, natural sources outweigh anthropogenic sources by quite a lot. We also talked about some of the sources of that natural aerosol, things like soil dust and sand, volcanic emissions, sea salt. From forests, you can have emission of organic compounds, things like isoprene and monoterpene. And then the chemistry that those compounds undergoes makes them less volatile. And so they condense into particles and form particles. So we can have kind of gas phase initiated particles too. And that's what we'll come back to for aerosol chemistry in the second half of the class. Anthropogenically, then we can have emissions from combustion engines, biomass burning, mechanically generated particles from mining or agriculture. And again, this kind of chemistry from the gas phase, this time with gas phase compounds that are released from car emissions or manufacturing, things like NOx and volatile organics. They can undergo chemistry, become less volatile, and condense into particles. So I want to talk about size distribution characteristics for 5 different kinds of aerosol, and then we'll kind of wrap up this size unit. The first is urban aerosol. And as you might suspect, urban aerosol are very high in terms of number, and that means then that they also tend to be relatively smaller than the particles found in remote areas. Urban aerosol is dominated by anthropogenic sources, and it's very variable in space. It depends strongly on our proximity to a source. So this is an illustration of that. from a 2002 paper. So you can see a nice kind of aerosol size distribution like we've talked about in class, where there's a logarithmic scale on the x-axis, and we're using a log input on the y-axis. And then this particular size distribution is multimodal, right? So you have 3 peaks, 3 places where you could fit a log normal size distribution with a mean and a spread. And so this particle size distribution is 30 meters downwind of a particular highway in Los Angeles. And then on the right is a size distribution, which is 150 meters downwind of that same highway. So only about 100 meters further. And you can see that the size distribution is quite different. It is unimodal. It peaks at much larger sizes and much lower numbers. I want to point out in particular that the y-axis only extends up to 6 on the right, and it extends all the way up to 20 on the left. So we have a lot more particles in close proximity to the highway. And then a very approximate loading for urban areas is between 50 and 100 micrograms per cubic meter. This would be a more polluted urban environment. In the US, our cities tend to have lower loadings. You can think of the values that you looked up in the AQLI database for comparison's sake. Then rural aerosol have relatively smaller sizes than the aerosol found in remote regions. So there's this kind of hierarchy, urban, rural, remote, where the particles are fewer and bigger as we kind of move through that hierarchy, urban, rural, remote. Rural aerosol are more dominated by natural sources with only a small anthropogenic contribution, and they're less variable in space than urban size distributions. So you see a kind of a comparison between urban and rural environments in these 2 size distributions at the bottom. We have a number size distribution on the left and a volume size distribution on the right. And then the urban environments are in red and the rural environments are in green. So for example, with number, you have a much higher number in the urban environment than in the rural environment. And it also is tending to peak at smaller sizes. Then for marine aerosol, this is more of a remote environment, right? So it's going to have fewer and relatively larger particles than the urban or rural environments. It has a larger contribution on a global scale in the southern hemisphere. The southern hemisphere is just dominated by more ocean regions. And an important distinction in thinking about marine aerosol is between sea spray and the marine boundary layer. So I have 2 size distributions here that I'm pulling from figures in Seinfeld and Pandas. On the left, you have the sea spray distribution. So this is just kind of wave breaking. And when that wave breaking happens, then sea salt becomes aerosolized. And so that is a fairly clean distribution. But if you look a little bit higher up within the marine boundary layer, then you get a size distribution that looks like the one on the right. And so it is more complicated, multimodal. And that is because clouds tend to form in the boundary layer. There's mixing in of other ambient sources of aerosol. It is not just cleanly this emission of sea salt. So yes, this is an important distinction for marine aerosol. Polar aerosol. This is again a remote environment, and so the loadings for polar aerosol will be much lower than, say, for urban or rural environments, certainly less than 20 micrograms per cubic meter. An important kind of feature of polar aerosol is strong seasonality. So you can see that here in pictures of a phenomenon that's called Arctic haze. And so we think of the Arctic as being this very pristine environment, but particularly during winter, when the air above the Arctic is very quiescent, it's not moving, there's not a lot of mixing and dynamicism, then the Arctic can have very low visibility and poor air quality. And that has to do with emissions that are coming from high latitudes, say biomass burning or other kind of manufacturing activity at these very high latitudes in Russia or areas like that. And the emissions from that activity are kind of swept up into the Arctic, and then because the air above the Arctic is quiescent, it kind of gets stuck there. So you can see the strong signal of this Arctic haze in size distributions over the Arctic, right? So the Arctic haze is in solid, and kind of the baseline clean Arctic is in this dashed line. So we get many more particles when this Arctic haze phenomenon is active. In general, polar and Arctic aerosol is a very active area of research, and this has to do with something called Arctic amplification. So the warming that is happening due to carbon dioxide emissions, it has a particularly strong impact over the poles and over the Arctic. And so it's interesting to sort of think about what role the aerosol play in the climate there, because it may kind of mitigate or amplify what is already intense warming at the Arctic. And lastly, desert aerosol. So this is sort of the kind of aerosol that would characterize Tucson. So desert environments have lots of small dust and sand particles, but the mass of these distributions is dominated by a few particles. So you kind of see typical desert aerosol number on top, surface area in the middle, and mass or volume on the bottom. And so the number peaks at small sizes, like we've said many times, and then for desert aerosol, mass is really strongly dominated by a few big particles. The profile aerosol that we have over a desert is strongly dependent on the wind and soil moisture conditions. We have strong winds and low soil moisture, then we'll get more aerosolized dust over our environment. And here you see a picture of a NASA model called GEOS-5, and it's aerosol optical depth. We'll come back to this, but optical depth is sort of, for now, you can think of it as the integrated amount of aerosol in a column. And where you see the orange color is dust. And so outflow from the Sahara is globally a huge source of aerosol in the atmosphere. It can extend all the way to Arizona and California, just huge amounts of dust aerosols from the Sahara on an annual basis. And the final factor here then is that mineralogy of whatever dust or sand is aerosolized is important. We'll talk a little bit later about ice nucleation in the atmosphere. Mineralogy is important there. And then when the dust deposits back down to the surface, it can deposit in the ocean, and it's important in that case for ocean fertilization.